we don't have to spend a lot of time on bio backgrounds because we have limited time, but working at Akamai 10 years, been doing web security stuff for over 20, lots of projects I've worked on in the past, and 2 books, shameless plug, Web App Defender is in the bookstore. Sorry.
Hello, everybody. My name is Isabella Barnett, also known as Angel Hacker. I'm a student at George Mason University studying cybersecurity engineering. I'm also a software engineering intern at DataBuoy, which does gunshot detection. And I've also earned 27 industry certifications, including Security Plus.
So an example we wanted to start with before we dive into anything actual Unicode related is real-world analogy. So we're assuming most everybody has played the telephone game, right? When you were a kid, you're at a party, and if you've never played it though, right, you come up with a phrase, you start whispering it in somebody's ear, they start whispering what they think they heard in somebody's ear. Usually along that path, because of errors, omissions, additions, or people trying to be funny, right, it changes. It finally gets to the end, and that person says what they think they heard, and it's usually quite different, right? Gets a good laugh at the party, right? So take this real world kind of fun game concept, but then we apply it to the web, right? So what we're talking about, a web telephone game. So think about the same scenario, right? You have somebody who's a web client, they're sending a request. There's always intermediary systems that request goes through before it gets to the application. So very, very simplified. But of course you have a CDN like us, Akamai, but then you have other proxy servers, other application servers, but we're kind of dealing with the same issue with the web requests. So one of the things that we've noticed when we were doing the research here, when I was gathering all this stuff, is the proliferation of bug bounty hunters. And specifically, Akamai customers embracing bug bounty, they have their programs. So we're in the middle of that traffic, right? You have bug hunters looking for what they're looking for. They got to come through us. And so we do inspection. So I got to come back so I can make sure on the slides. There we go. So when we're doing the inspection, we are looking at it in flight, right? We're going to look at it, see if we see anything bad, and then we'll do whatever the customer asks us to do to block it, alert, whatever. And then it goes on inside the customer's application. They're probably doing similar types of security inspection, whatever that may be. The key issue, though, is when we look at it, it's not bad. It's not malicious at that point. It's not functional code that's going to do something. When it makes it inside the application after the security logic, something happens. Data's processed, manipulated, changed, and it actually then becomes malicious. That's where you get into the big problem. So the quick takeaway, number one thing from this entire talk, it's CWE 180. If there was one thing you remember, it's this. You've got to make sure you're normalizing data into whatever form it's going to be, then do your security checks. So what we'll be talking about are all sorts of scenarios where this was done incorrectly. All right, so quick agenda. Of course, we're going to go fast based on time, but these are the things we're going to hit on today. And what I did is got information from work at Akamai, sanitized, of course, and then made it into little mini research projects that I worked on with my daughter. Say, hey, here's a problem. Let's go research. Let's find out why are these things happening. Let's find out tools that look for this. If the tools aren't updated, let's update them ourselves. So, next.
And then what I've done is, Yes We Hack has a Dojo Lab program where you can create your own labs and it can simulate different process flows. And what I've done is recreated some labs for the different topics we're going to be talking about. Here's a QR code if anyone's interested in trying out these labs on your own. Since we don't have enough time today to go over each one individually, we thought this would be a good take-home lab. So first up, we're going to go over Unicode, specifically internationalization. So this is the process of making sure that computers around the world can handle all these different character sets and languages and glyphs and symbols, and making sure that they can communicate together. So here's a UTF-8 visualizer made by Sonar Source. It's a great source you can check out. And first up is the Unicode code point in white. This is the numeric representation of the glyph. Next is the raw bytes. This is the binary, and it's going to be how it's stored in a database or in memory. And then finally is the UTF-8 encoding. This is how it would be sent over the web in a web request. And since Unicode is such a broad topic, we don't have time to talk about everything today. We're going to focus on the 3 key points that are critical to our talk. First, Unicode is representing a lot of characters from around the world, and it can be multi-byte. However, ASCII is a subset that is only single byte, specifically 7 bits. So you get into issues then when you're trying to convert between Unicode and ASCII, and you want to maintain data integrity. First up, we have decoding errors, specifically multi-byte awareness. You get into CWE 172, which is about encoding errors, but also decoding errors when you're decoding and your output is not the same as the input, if it's garbled text, any way it's been changed. Again, with the visualizer, you see here, there is an ASCII, capital letter A, and then the multi-byte laptop emoji. The leading bits will signal the character byte length. If it's a 0, that means it's single byte. As you can see here, it's 4 leading 1s, which means it's going to be 4 bytes long. And then continuation bytes have a 1 and a 0. And this signifies that these bytes are all connected. They're working together to represent a single character. But what if an application doesn't understand that? If it's not multi-byte aware, it might treat these 4 bytes as separate and change the leading 1s to 0s. Then you get something called mojibake output, which is Japanese, roughly translates to character mutation. As you can see in this little video, it's changing the leading 1s to 0s, and then you get 4 separate characters that have no relation to the original character. Here's a great tool. Burp Suite can be used to test web applications. We're going to be using it today. Let's say we want to input this left angle bracket, and we're going to take the UTF-8 encoding at the bottom, representative of the 3 bytes. If you put it into Burp's decoder, because it is not multi-byte aware, you get the mojibake output, 3 separate Unicode characters that have no relation to the original input. But you can get the decoder improved, which has Unicode support. Because of the Java swing elements, it can properly render and display these Unicode characters. There we go.
Finally working.
The decoder improved is multi-byte aware, and it can correctly decode it into the left angle bracket. We've also made various updates to Activescan++. These updates were released today, so you guys can check them out for testing various things that we're going to be talking about today.
So you can talk to it.
Oh, these were supposed to...
Oh, is this a different one?
This isn't...
That's right, just click ahead.
We don't have time to talk about all the updates here, but...
Yeah, we had a condensed version, so there may be some extra slides in there. So the next thing is still talking about decoding problems. The other scenario is overlong encoding. So it's a different scenario. You got to make sure you get this right, otherwise any of your security checks will not work. So KPEC 80 is what we're referencing here. So another real-world analogy for you, right? If you've ever received an Amazon package, you open the box, there's packaging, and then there's another Amazon box inside, and you're like, why didn't you just send me this box? So it's needless packaging. So that's essentially what we're talking about here with overlong. So you have an ASCII capital letter A, it's represented as a single byte, but you can technically change that and represent it as 2 bytes in an overlong format, which is what this is showing. The issue is because of what Isabella was talking about with the bytes, you have continuation bytes, and the bits 1 and 0 at the beginning mean that they're together. So originally you were using 7 bits of the byte. If you want to then make it overlong, you have to take a bit of data and move it, right, over into a different byte. But this is still representing the same character. The question is, anything in your applications, what are they going to do with that? Because UTF-8 originally allowed this, but then they realized this could cause problems. You're not supposed to do it anymore. You're supposed to use non-shortest form. So what is an app going to do? Is it going to block it? Is it going to normalize it? What's it going to do? All right, so overlong format. When I was looking at this and we were researching and talking about it, I said, wait a second, I have seen this before. So if you take the // and then you look at the bottom and you think about UTF-8, if anybody was doing web security in 2001, I was protecting government websites at the time, and I saw stuff coming in saying, what is this? Okay, this is going on, this is the NIMDA worm. So if anybody remembers these, also if you went to the keynote with Miko, he was talking about these types of things with Slammer and all the Blaster, and this was one of the things that happened at the time. But it was leveraging this overlong encoding. It would take the dots and forward and back slashes. It would overlong encode them. Security checks wouldn't work. And then it would properly decode it, and then it could get to a command prompt and propagate. There we go. Some other practical examples that I deal with here at Akamai is scenarios with SQL injection as one tool example. This is SQL map, largely used in SQL attacks. They have a capability called tamper scripts. You can do all sorts of obfuscation of the payloads. This is one which is for overlong, where it'll take a regular %20 space character, overlong encoded into 2 bytes, right? So if we go forward, so this is another example. You can just take this as an example of doing any kind of quote unquote security check, right? So here we're leveraging an online tool to do red checks and validations. So we're passing in the URL bar the exact thing that SQL map was doing, right? And then we have a very generic basic regex, which looks for select and from, and then in between you can have a space character and then some non-space characters. The problem is this regex does not match that content. So you have a mismatch. Think about evasion scenarios. The question is, why did this not match? The problem is a combination of overlong encoding and what Isabella talked about, mojibake. Because if you look down here, you'll see there's actually replacement characters that it did not properly decode it back to the space character. It says, oh, these are 2 bytes long, but if I treat those as ASCII, they're not visible rendered anything, so it puts these replacement characters in.
Next up, we have byte truncation. So for our case study, we're going to be talking about how a bug hunter found control line feed injection in Microsoft. As you can see here in the input, there was a carriage return and a line feed UTF-8 encoded. But if you submit this as expected, access denied, it would be blocked. But you can see here, they've submitted 2 different characters, UTF-8 encoded, and then in the response, you can see the set cookie header has been successfully injected. How did they accomplish this? If you're using the CyberChef tool, you can do a URL decode, and as you can see here, you get 2 Chinese characters. This is obviously not control line feed, so how did this get converted? What is going on here? Now, this is a potential situation happening on the server side. Most of these are black boxes, so you don't actually know what is happening, but this is a potential scenario. If they're doing little endian byte ordering, they're going to take the least significant byte, byte 0, and store that first. So using our example with the Chinese character, if you have a single byte buffer, perhaps the application only handles US ASCII, it's going to take those 3 bits and store byte 0, but that fills the byte buffer. The other 2 bytes are discarded, and then you're left with this single character, which happens to be the carriage return. So byte truncation is the reason that you're getting the control line feed. As you can see here, if you perform an encoding of US ASCII 7-bit, you will get byte truncation, and you'll get the control line feed characters before the set cookie. And then we've got a bunch of tooling that if you look at our talk, you can see it later, but we have to skip through because of time. But we've updated Activescan.
Yep. All right, next one is Confusables. Generally, when you talk about Unicode, people immediately think about this. Characters that look alike. Usually this was in phishing websites a long time ago, right, with domain names, but that's not really what we're talking about here with this use case. Okay. An example on the globe, right? Let's say there's somebody in Greece. They're sending data across to somebody in the US. They're sending Greek characters, like Greek capital letter alpha. The question is, again, on the receiving side, we only handle US ASCII. We do not have that character. What do we do? So generally speaking, I don't have that. I have a different character that looks kind of similar. So I'm just going to change it, use this character instead. And that's not going to cause a problem, right? Right? But of course it does, which is why we're talking about this. Normalization forms. When you hear Unicode normalization, this is generally what everybody thinks about. Again, we can't go over all 4 of these. The top 2 we'll touch on briefly later. The bottom 2 are what's really important for Confusables. It's compatibility, which means Confusables, lookalikes, or best fit mapping. All 3 of those are kind of similar. Also, we're highlighting here the second to last row, where you have the 1 that's in a circle. Those are called enclosed alphanumerics. We see these a lot in server-side request forgery attacks for a way to evade some of the filters that may be in place. So as an example, going back to the Unicode site, they have capabilities where you can test all sorts of things related to Unicode. Here we're putting in an example if an attacker was trying to do SSRF with the loopback IP, but they know it could get blocked, they may do it in an enclosed alphanumeric form. But then if you look at the bottom, the different IDNA processing output, depending on what's in use, you can see some of those will translate those back to normal ASCII characters, which then ends up working. So as an example, if I were to kind of mimic this just command line using curl, because a lot of times in the web servers, when you think about SSRF scenarios, it's going to take data and do a sub request call, often using things like libcurl. So this is a good way to mimic that kind of behavior. So you can see I'm making a call, but I'm using that enclosed alphanumeric form. But as you can see, based on the libraries that are actually compiled in my version, kind of funny note, my daughter was testing, it didn't work for her. So it depends on the libraries that are installed in the IDNA processing. But in this case, it does actually resolve it, right? And then it would work and it could go to the loopback IP. All right, so a good quick case study talking about Unicode normalizations. I'm going to step off to the side so you can see. This was Searchlight Cyber. I think they actually have a booth somewhere around here. Fantastic research that they do. This was a Unicode issue with .NET Nuke that this was just released about 3 weeks ago. All right, so a big slide. If you're not used to looking at raw web requests, maybe it doesn't mean too much, but this is doing a post request with a multi-part body and it's attaching a file. Now, for the rest of this case study, we're really focusing on the file name itself. And you can see some of the data in there is UTF-8 encoded because it's using these different Unicode characters. So keep this in mind. This is how it's received by the application. So if you do the UTF-8 decode and you look at the raw data that's there, you can look what we highlighted. Visually, they look like backslashes and dots. They're not. They are the Unicode full width versions of those. Those have different meanings. But keep this in mind as we go forward. All right, so now we're jumping into a small section of the code. So remember at the beginning, we said CWE 180. You got to do normalization first, then your security checks. So here, they are doing a security check on the data we just saw, and it's applying a regular expression to say, hey, look for any dot characters. If you see a dot that's not at the end related to the file extension, strip those out. So it's doing a regex replace. But if you look at what's at the bottom, regex does not match, right? It's not those ASCII characters. So this regex check fails. It didn't sanitize anything, and then it moves on in processing. So you can probably guess what happens next based on what we've been saying. Now it's going to run a Unicode normalization. Now on Microsoft, a lot of times it's called best fit mapping. They're applying different code pages depending on how they want their application to work. And in this case, it was using code page 1251. So now we can go and look at the Unicode site, and they have all of the different code pages, right? So you can go look these up and see what these mappings are. So it is a normalization, but Microsoft does a little different where they're doing this direct mapping of certain characters to other ones. So the ones we highlighted here in blue, as you can guess, these are going to match. The full width stop translates it into the normal ASCII stop character. And so then you have the final payload here at the bottom. So this is after the security check. So of course, that would have matched the regex. They did it at the wrong time. They got the ordering wrong. The other thing to notice is now that these are double backslashes at the beginning and it's a Microsoft system, oh, absolute path, right? UNC, I can connect to a system. Let me find the host name. Starts to then process that, and you have those extra dots that should have been stripped. And so now it goes to this OASTify out-of-band beaconing domain, makes an outbound connection, and leaks Windows credentials. So that's what they were doing in this write-up. Again, due to time, we can't show other stuff. Quick reference, another great one by Orange Tsai, great researcher. You can go check out that worst.fit website. All right, well, again,
More Activescan.
Yeah,
we have to skip this.
Jump these because we don't have time.
We made lots of updates.
All right, next to last section, casing. This was one that I ran into. Also, my colleague Sam, who's here, we ran into these at work. We get these reports from customers. There we go. Came in through HackerOne. He said, hey, you didn't block something. You know, what is this? Why is this working? We were scratching our heads a bit because, yes, of course, we're well aware of these Unicode-related issues. And this didn't match things that we were normally seeing. Say this shouldn't be translated in the way that it was. So we're saying, what's happening here? So these characters, right, if you decode this, you can see it's a long name. So Latin small letter dotless I, right? If you decode that, it looks kind of like a script tag, but in a browser, that's not executable. That is not a script tag. We were looking for certain things like that. That is not a script tag. On you go, right? All right, so now we're referencing what we've talked about before. You have any type of security check. If it's doing a basic thing like that, okay, it's not going to match. Move on. So what we finally figured out was casing problems. So think any application that may be applying things like lowercase, uppercase, case folding, title case. There's weird edge case scenarios where certain characters like this exact one will then become an ASCII capital letter I. So working with Izzy, I said, hey, write up a Python script that mimics what we're talking about here. So she went ahead and did that. We were able to decode it. We're applying the upper method, and then we're going to compare both those outputs. So as you might expect, oh crap, you take that I, it becomes the capital letter I. Now here, of course, everything is uppercased. So there is some limitation in what's actually executable, what will work. But it's very interesting, right? This scenario that you can get around certain things.
More updates.
Yeah, more updates. Go. Oh, Activescan and also Recollapse. Go check out those tools.
And now, best for last, we have combining diacritics, also known as combining characters. So if you have a normalization form here that's doing decomposition, it's going to take this character and separate it into two separate code points. So we're going to talk about this zero-click account takeover as our first case study. As you can see in this flow chart, this is how a normal password reset would go. A user would submit their email. It goes to the server and gets passed back to the database, who would perform a check, say, yes, this is a valid user, and it would return a token so that the person could reset their password. But let's take a deep dive into that MySQL database and what it might be doing, and specifically what kind of collation it might be performing. And in this case, it's the 0900. That's the collation algorithm version. And then you have AI and CI, which means accent insensitive and case insensitive. Let's find out what that means exactly. So here, if you're comparing the lowercase a with an accent to another ASCII lowercase a or an uppercase ASCII a, it would tell you, true, these are exactly equivalent. They look identical to me. But on the other hand, if you do accent sensitive and case sensitive, as expected, false. They are no longer treated as the same. Back to our flow diagram. If the attacker submits this email with a custom domain that has a Unicode character and passes it onto the database, it says, yeah, according to the collation algorithm, the Latin small letter a with a double grav is completely identical to the Latin small letter a. And because it's equivalent, when it checks in the database, it says, yes, this is user@gmail.com, and it's going to submit that token, and here's the issue. It submits it back to the user email that was supplied, not the email stored in the database, and thus the attacker now has a token to reset someone else's account. Unicode has these great collation charts that you can look at, and you can see here how the lowercase a can be collated and treated as equivalent to all of these different Unicode characters. And for our final case study, XSSE has a really great lab that we're going to explore a bit. As you can see in the top URL bar, there is the name parameter. We're submitting this Unicode character with an accent just to see, oh yes, they're probably doing some sort of normalization composition form as it is properly rendered. And then if you look in the HTML source code, you can see at the bottom here, there's this text area tags, which happen to be container element. And the parameter input is being placed in between the text area tags right next to that greater than symbol. So if we look on the back end, the free marker, you can see that our input is being concatenated with the tag, and then all of it is together normalized. So our goal is to try and change that greater than symbol with our input. So to accomplish this, we are looking for a specific character that when concatenated and combined with the greater than symbol, changes its identity. as you can see, we have figured out it is this character, which is the combining long solstice overlay. So this combining character, when concatenated with a greater than symbol, creates not greater than. That modifies the character completely. It's a completely separate code point, and thus we can use it to exploit this lab. We're going to take the UTF-8 encoding of the combining long solstice overlay, and we're going to put it at the beginning of the name parameter. Now here's a little aside, something we found interesting. The browser is properly rendering this combining character with the equal sign to create not equals, so that's a little fun visualization of what we're talking about. But if you submit it at the beginning of this name parameter, you can see in the source code it becomes not greater than. You have broken the beginning of that text area tag and injected the onFocus event handler and the alert pop-up with a document cookie. And as you can see, cross-site scripting. More tooling updates.
All right. So to wrap up, some things to take away. As we were mentioning, the number one thing is getting the ordering correct. Normalize data first, then do security checks. Seems obvious, but as we're showing, happens all the time. There's different ways and places where this still may show up. Validate URL decodings. As we showed at the beginning, if you don't get that part right, everything behind it gets stuck. So make sure you do that. And normalization forms, try and find out where those are. The problem is talking with other security researchers, people here at the event, it's very hard to identify. That's why we were updating tooling, right? You may think you know, it may be in documentation, you may update a library, it's doing something you didn't know. Use those tools to assess your environment so you're sure where all that stuff is. So with that, we're done, and we can take any questions, but thank you for coming.
Thank you.